I trust you.
Okay, so I want to continue our lesson where we started.
Nu ska du inte göra.
Men vill du? Jo, det
Okay, so if you remember, we started talking about the notion of the area. I wanted to motivate you about the definition of an integral, and then we learned that. So if you remember, I started from this to motivate you with the definition of an integral. So I told you that usually we were interested in calculating the areas, okay? And then we started subdividing this area below the curve into small rectangles and add the areas of those rectangles, so to calculate an approximate value for the area. Yes? And then I hope that I could convince you that if you make these rectangles finer and finer, you will get a better and better approximation to the area under the curve. Yes? So in principle, if this is my point A, this is my point B, if I am interested in this area, yes? So I started partitioning this interval to the small sub-intervals, for example. This is the kth interval. If you remember, it starts from x sub k minus 1 up to k. This is called the kth interval. Then in that language, I denote this by x naught, and I denote the last one by xn. And I told you that the difference between these, the length of each sub-interval, we call it delta x, and it is clear if I subdivide them into equal pieces, then the length of each sub-interval is the total length of my interval divided by the number of partitions that I want to do that. And then we learned that if I want to calculate xk, if you look back to the formulas we had, I have to start. If I want to go to the next point, I need to add 1 delta x to it. If I want to go to the second point, I need to add 2 delta x's to it. If I want to go to the kth point, it means that I need to add k delta x to that. Yes? And that was the formula we got for these numbers. And then delta x is here, so you can combine them. And you can find the formula xk, which is equal to a plus k times b minus a over n. So that is your formula for each one of these points. And then we learned that if, for example, if you concentrate on this sub-interval, and then in principle, you can choose any number within this interval, but I talked about choosing a number which makes the function minimum in that one. In the book, they are talking about the midpoint, and it doesn't need to be midpoint. You can choose whatever you like in this interval. If this function is supposed to be what we call integrable, if this is going to work, it doesn't depend on the point that you choose within that interval, okay? So here, let us concentrate on choosing the value in this interval so that this is the kth interval. The kth interval, the kth sub-interval is this interval. X starts from xk minus 1 up to xk. In principle, you can choose any number within this interval, but I told you that let us make the minimum. Let us choose ck, a number here, so that makes my function minimum. So for example, in this picture, this would be this point, yes? So in this picture, ck is equal to x sub k minus 1. And then when I make this rectangle, if I ask you how can I calculate the area of this rectangle, you would say that if I want to find the height, I have to calculate the function. If this is function f, I have to calculate the function f at that point and multiply it by the width of that rectangle, which is delta x. This gives me the area of this one single rectangle. And I have another rectangle on the next interval, yes? I have another rectangle here. If I start summing them up, k goes from 1 to n, if I finish that, this gives me an approximate value to the area that I want to calculate. What I am doing, I am adding the areas of these rectangles. Of course, it is clear I am just ignoring this part, I am ignoring that part. But these parts that I am ignoring, I was able hopefully to convince you that they become smaller and smaller if the number of partitions go higher and higher, yes? And in principle, if I do it infinitely many times, then hopefully you agree that these are actually negligible. And then we say that if I set the limit of this expression when n goes to infinity, then the answer becomes equal to the area that I want to calculate. So what I wanted to do, I just wanted to motivate you about this particular limit. So exactly when I was teaching you the derivative, I started with a simple question. I told you that, okay, I have a curve. My question, Leibniz's question was, how can I find an equation for the tangent line? This simple question gave rise to calculating a limit f of a plus h minus f of a divided by h when h goes to 0, yes? So this type of limit came out when I was talking about this. And then I told you that Newton was talking about a completely different problem. He wanted to measure the instantaneous, to calculate the instantaneous velocity of a moving particle. He also came up with the same structure limit. So when this happens, one thing happens in two different areas or more than two different areas. So people start thinking that might be this is a very deeper problem in our nature. So let us investigate on it, give it a name, try to understand its properties and etc. So that was the starting point. This limit was important and it happens in different areas. So mathematicians chose to start investigating the properties of this limit, and it gives rise to the whole idea of derivative and what we have studied so far. Yes? And now the same idea happens here. This is a very tangible question. I want to find the area. If I want to find that area, it turns out that this limit is important. Yes? So this is probably, we were not able to guess this limit if we didn't have any motivating problem in the beginning. This was our motivating problem. It gave rise to this limit. And now this limit, by the way, can also happen in another part. For example, even in physics, mostly actually. So for example, if I give you a particle is moving with constant speed, constant velocity, let me call it 2 meters per second, and I wait for 10 seconds, how much this particle is displaced? Assume that this is the velocity, so it is going positive. It means that it is going always to the right. There is no change in velocity. It's always positive, but it is a constant velocity. And I wait 10 seconds. How much this particle is displaced during these 10 seconds? 2 times 10 is 20. But now assume that this particle is not moving with a constant speed. That the speed of the particle is all the time changing. So for example, if I ask you, this particle moves in a way that its speed, its velocity at time t is 2t squared. Okay? And then I am asking you the same question. I wait 10 seconds. How much this particle is displaced? It's not as easy as answering that question. Yes? Is that understandable? Now let us try to solve this problem. Okay, in principle, instead of giving you different functions, let us just work with the function v of t. Any function. Now I am waiting for, I don't know, a period of time. For example, I wait from 0 to some later time, let us call it capital T. And I want to ask the same question. How much the particle is displaced during this time interval from 0 to capital T? How can we answer that? Because this particle is not moving with a constant velocity, the velocity is changing all the time, okay? But physically, if I make the interval short, the interval that I am looking, so here, let me call it the t-axis, the time axis, and then what I want to do, this is, for example, 0, and this is the final time t, okay? Let us start dividing this interval into smaller pieces, this time interval, not x interval, yes? And then what happens, if I, for example, start dividing it to, for example, let me make it 4 pieces, okay? Of course, when the particle is moving with a different velocity which depends on time, still I cannot make sure that the speed of the particle is constant here. Do you agree? Because it's still changing. But, so if I ask you, can you give me an approximate value of the displacement, I can imagine that the value of this speed, of this velocity on this interval is a constant. Okay, this is of course not reality because it also changes. So, but I can assume that the value of this speed over this interval, that interval, that interval is a constant. This constant might be different from this constant, but I could assume that the speed of the particle is constant here. So what can I do? I can take the speed of the velocity, say for example at point 0, and multiply it by this time interval, let me call it delta t. It gives me an approximate value of the displacement during this interval. Do you agree? It's not the exact one because this is approximation, but I can do it for the next time. For example, if this is t1, I can calculate v at t1 and multiply it by delta t. It will give me another displacement on this interval. Yes? And then what I can do, I can continue, and then I add them together. So you see the structure that appears is very similar to this structure. Instead of function f, I have function v. Instead of a number ck, I have a number 0, t1, etc. Instead of delta x, I have delta t. And if I start adding them, so it becomes sigma v of some number ck, for example, times delta t. Yes? This would be an approximate value for the displacement. But now imagine, we are living in this universe, we have a lot of intuition about how things work. So if I make this interval shorter, what happens? The particle doesn't have enough time to change its speed, yes? So if I make this shorter, I would say still the velocity would be different at different times, but they are closer together because the particle didn't have enough time to change its speed, yes? Is that understandable or not? If I give you a very short time, then the change in the velocity of a particle cannot be very big, yes? Even if it is big, you can make the interval shorter, yes? Even if you are working with photons, which actually move at the speed of light, if you make this incredibly short, then even photons cannot display that much. If I give you 0 time to a photon, the displacement for the photon would be 0. So I can make this distance very, very short. The change in the speed very short, of course. But what I'm saying is intuitively, if I want to ask you how much this particle is displaced, you would say that, let me calculate this thing, yes, and then take the limit of this when n goes to infinity. N goes to infinity, it means that I am making these intervals extremely short so that the particle doesn't have enough time to change its speed during that very short interval. So you see that, what is the difference between this structure and that structure? Mathematically, they are the same, yes? I have a function. Here it's called velocity, here it's called just a function, and then I have a short interval delta t, and I have here delta x. So you see that the structure again appears in that different area. That's a physics problem. That was a math problem. But again, this happens here and there. I can give you a lot of examples of that kind, for example. Let us just stop here. I just wanted to motivate you. This sum this limit is an important limit, okay? And when it comes up, mathematicians try to give these kinds of sums a name and try to study their properties, okay? And then this sum is called the definite integral of your function on that interval. Is that clear? Yes or no? Yes. So I just wanted to motivate you very crudely that this limit is important. Okay, by giving you two examples, one in physics, one in mathematics itself. Is that clear? Okay. Now, this limit, by the way, these sums are called Riemann sums, if you remember. Genius German mathematicians. These are called Riemann sums, and the limit of a Riemann sum is called an integral. Okay, integral of the function on that interval. But before doing that, before doing a formal definition of that, if you remember, I told you that, first of all, this is practically very hard, even though in principle it is completely intuitive and you understand that. But using this for practical purposes could be extremely hard and most of the time impossible. I gave you an example that we calculated the area. Do you remember the area of a triangle using that? That was, of course, a very trivial thing because you didn't even need the integral to calculate the area of a triangle. You already knew the answer. But let me give you a little bit more non-trivial example today. Just practice a little bit about this. I want you to see it. I don't want you to learn it if you don't like it, okay? This formula is in the book. I want to talk a little bit about it, around that to understand it. Then we will start formally talking about the things that you have to know. Okay, so let me give you another type of these problems. You can just look, and if you like, hopefully you will enjoy it. If you don't like, you can, 15 minutes, you can have a nap and then wait on it, okay? Okay, so what we do is this. We want to calculate this area. By the way, Archimedes 400 BC was able to do this. Okay, so that is actually this idea. The first probably who invented integral calculus was Archimedes. So here, assume that I give you this function, y equals to y minus x squared. And I want to find the area below this curve between 0 and 1. Okay, so if you draw the graph of that, do you know how is the graph of that? This is also very good to know about this. What is the graph of x squared? Everyone knows. Yes? This is the graph of x squared. If I ask you what is the graph of negative 1y is x squared, you should know. What is that? Well, it's flipped. Yes? So this is the flipped. And then I add 1 to it. So it means that I'm shifting it up. So you don't need any calculator to understand that. So that is the same parabola flipped about the x-axis and shifted 1 unit upward, yes? So this would be this graph. So let me exaggerate a little bit. Let me concentrate, this becomes 1, and let me draw this, okay? Because I want to have a bigger picture. So this is 1. Okay, now tell me, what is this number here? Might be my graph is not into scale, but yes?
The root. Oh.
So what's that? It's 1, yes? You put y equal to 0 to find x. You get two values. X is plus or minus 1. Minus 1 is definitely this one. Positive 1 is definitely that one. Yes? But let me forget about this part and just concentrate on calculating the area here. Okay? So I want to calculate this area. From here up to here, below this curve, above the x-axis. Okay, so what is the formula that I have so far? The formula that I have, area, is equal to the limit of sigma, k goes from 1 up to n. Do you remember? F of ck. Here I have chosen ck so that it gives you the minimum value. In principle, you will study later in the university that if this function has an integral, it doesn't depend on which point you choose. Okay, so you have infinitely many degrees of freedom to set up this. You can choose whatever you like in one of these intervals, okay? But those are more advanced topics, forget about them. So let us calculate this. Okay. So can you tell me what is delta x here? I wrote the formula and I erased that. Hopefully you know that. What is the formula? It's b minus a divided by n. So what is b in this problem? The final point of my interval. The initial point I want to consider because I want to calculate this area. I don't want to go beyond that. So it is 1 minus 0 divided by n. So this means that my delta x is 1 over n. Is that right? Okay, but let me concentrate on the kth. Yes? Is it wrong?
Shouldn't it a be minus 1? Or
A b minus 1? No, b minus 1 is the length. This is my delta x. This is the subinterval length. Okay, and then what should I do? Concentrate only on the kth interval. Do you remember what is the kth interval? The kth interval starts from subpoint x sub k minus 1 up to xk, and then let me concentrate on this. Of course, it is supposed to be extremely narrow when I make n infinitely infinitely big. So, and then can you tell me what would be ck in this interval for this function, assuming that ck is the one which gives you the minimum?
XK.
It's xk, yes? So you see that within this interval, the minimum actually occurs at this endpoint. So here, by looking at this, I realize that ck is just xk. Yes? And now, let me ask you, do you remember I wrote something here for you? What was xk? I remind you of that, reminded of. It's a plus k times delta x. Yes? And then what is a? A is 0. So it is 0. Plus k is just k. Delta x I calculated here. So this means that xk is equal to k over n. This is my xk. Okay, but now ck is equal to xk. Let me just describe it once more. When I was teaching, I told you that I want to choose, there is no obligation about that, I want to choose ck, the value on this interval, so that makes the function minimum. And you see that in this interval, because of the nature of decreasing nature of this function, the minimum occurs at the right endpoint. So ck is xk for this function, yes? And then I am saying that I want to calculate f of ck. So what is f of ck? This is my function f of x. So f of ck becomes 1 minus ck squared. This is f of ck. And then ck is equal to xk. So it's minus xk to power 2. And instead of xk, I put its value. So it becomes 1 minus k squared n squared. Yes, understandable? And now I put everything inside this limit, hope for the best that I can calculate this limit. And I will tell you why calculating this limit is hard. Okay? It becomes sometimes impossible to calculate this limit by limiting process, okay? So then it becomes limit sigma, k goes from 1 to n. Okay, so you can help me here. So f of ck is this expression. So let me write it down. 1 minus k squared over n squared. And then multiplied by delta x, but delta x is 1 over n. Yes, so this is the formula that I hope that I can calculate. If I can calculate this fairly complicated limit, then hopefully I can solve the problem. Is the structure here clear for everyone? I just did it step by step. Now, just forget about everything. This is the way that you need to learn in mathematics. When I am solving this, I don't care about what's happening before that. I just focus on just calculating this. And of course, in the middle, I have to have an open eye to see that if the numbers and everything that I am getting is reasonable. Okay, so do you have any suggestions how to calculate this limit? This is not a standard lesson for you, but it's not that hard that you don't understand it either. So first of all, you need to have an understanding of what is going on from this limit. Yes. So if you don't mind, I would multiply this. This is natural idea. Yes. I multiply this in. So it's what happens. Yes. Or yeah, that's good. So let us do it. So this becomes the limit. Sigma k goes from 1 to n. And then let me multiply 1 over n inside. So it becomes this k squared over n to the power of 3. Okay, and then what we have to do, because your knowledge about sigma is probably a little bit limited, so the best thing that you can do is open up the sigma to see what's going on. Yes? Otherwise, you can use the properties of sigma to calculate it a little bit easier. But don't worry about that. Let us open up the sigma. So I copy and paste this limit all the time. So my goal is to open up the sigma, but this is at the level of your knowledge exactly. So how can I open the sigma up? I have to put k equal to 1. I have to put k equal to 2, and until I put k equal to n, and I find these numbers and add them together. Yes? So let us see what happens. If I put k equal to 1, this doesn't depend on n. So I would write 1 over n, and I put k equal to 1. Intentionally, let me write it y to the power 1 to power 2, even though 1 to power 2 is, because I'm looking for a pattern, so let us keep the pattern. Is that clear? This is the one that I put k equal to 1. Then I put k equal to 2. There is nothing related to k here, so I would write it here. And then this becomes 2 to power 2, n to the power of 3. And then let me write the other one, 1 over n minus 3 to power 2, n over 3. And can you tell me what happens at the end? What happens?
1 over n minus n squared over n cubed.
Thank you, yes. Even though, don't be in a hurry. When you want to find a pattern, don't pay attention to simplifications that much. Of course, I can simplify n squared by n. The last term is, of course, 0. But don't pay attention to that. It is not wrong, but your goal is to find the pattern. So don't do these simplifications, okay? But then how many pair of brackets do you see here? Can you tell me? How many pair of brackets are there? N number, because I go from 1 to n. Yes, so there are n pair of brackets. So I have 1 over n here, 1 over n here, 1 over n here, and 1 over n here. How many times? N times, yes? So let us now start simplification. So 1 over n, 1 over n, 1 over n until the end, it becomes n times 1 over n. Do you agree? Because all of them are the same. But this one and that one and that one and that one, the good point is that all of them have a negative sign, so I can pull the negative sign out, and all of them share the same denominator. So it's not that hard. So let us just write it. Okay, how should I write it? I write it as one fraction whose denominator is n to the 3, and the numerator becomes 1 to the 2 plus 2 to the 2 plus 3 to the 2 up to n to the 2. Is that understandable? And then, of course, n goes to infinity. Is it clear what I'm doing? Okay, so then n times 1 over n is super simple. It's just 1. I don't know if you have seen this formula before. When I was teaching you mathematical induction, this is one of those examples in Math 5. And still, if you go to that problem, there is a formula for that. This is the hard part. If I make the function complicated, then calculating this sum becomes impossible. But this is, we are lucky, this function is so simple that this sum can be replaced by a closed formula, not including these dots. Okay, so what I'm trying to say is that we had this formula in Math 4, in Math 5, and if you want, you can prove it using mathematical induction. The answer to this is n times n plus 1 times 2n plus 1 divided by 6. This is also a famous sum. And this is an exercise. If you have forgotten, you can immediately use working it out with mathematical induction. It's a very simple exercise in mathematical induction. So I am allowed to use that formula there. So this becomes, instead of this sum, I can write a closed formula. Closed formula means a formula which is equal to that without the dots. Yes? And now let us see what happens. Here, what I do, one of these ends, and one of these ends are gone. It becomes n squared, and this 6 will be multiplied by the denominator. So this becomes n plus 1, 2n plus 1, divided by 6n squared. If you have doubts about that, please let me know. Is that understandable? This is a simple calculation. I'll just simplify this n. This n is gone. From this, n 2 is left. But I give a denominator 1 to it. 1 times that goes to the numerator. 6 times this goes to the denominator. So you see that now everything is more or less settled down. It's not a wild problem, so I can immediately try to answer what's happening there. Okay? Okay, so let me tell you how we can calculate. Do you have any clue how to do this? This is not a standard one for you, but it's not that hard. So I write it in this way. Just tell me, do you agree with me or not? I write it in this way. Do you agree what I have written here is exactly that expression? Yes? Because here, multiply this by that. 6 times n becomes 6n squared, so that's valid. And then 1 times this times that becomes exactly the numerator. Understandable? That's exactly the same thing. But what is the benefit of that? You will see in a while. So the benefit is that I can write it in this way. Just confirm that you agree with me. So 1 over 6, I write it as 1 plus 1 over n times 2 plus 1 over n. Do you agree with this one as well? Yes? Because what I have done, I have split it into 2 parts. N divided by n is 1. 1 divided by n is 1 over n. And I did the same thing here. 2n divided by n is 2. 1 divided by n is that guy. Understandable? Okay, why this is good? Because I am sending n to infinity, and you know what will happen to this guy and that guy. When n is extremely large, what happens for 1 over n? It becomes 0. When n is extremely large, that becomes 0. And then I calculate. So this is constant, minus 1 over 6. This is 1 plus 0. This is 2 plus 0. Let us calculate this. This is a simple calculation. 1 times 2 is 2. 2 over 6 is 1/3. So it becomes 1 minus 1/3. And what's the answer? It's 2/3 area unit. Yes? So you see that it was doable, but it is very tedious if I want to calculate this. Is that clear? Now you learned how to do it in Math 3C. There is a theorem called Newton's theorem. He came and said that actually how to calculate this. And then it is not just practically important, it's theoretically important, because you agree with me that if I make this function harder, for example, if I put sine function here, then what appears in this series is a series of sine functions. Then I don't know how to add them. Yes, I don't have any closed formula. I don't know if I have a square root function, as simple as that. Forget about trigonometry. 1 minus the square root of x. Then what I will get here is a square root of 1 plus a square root of 2. There is no closed formula for that. So this would be a dead end for this naive way of doing calculations. But Newton actually realized a very important thing here, and I will come up to that. So he said, instead of doing this mess, I realized you can just find a primitive function for this. So this is the first time we see the connection between primitive functions and the area. It was totally unrelated, yes? So here, if I want to calculate a primitive function, can you tell me what's a primitive function for that? It should be very easy.
X minus x to the 3 over 3.
Yes, exactly. So that is a primitive function. Newton taught us actually, put these numbers 0 and 1 here and subtract them. So you put just 1 here, what happens? It becomes 1 minus 1/3, it becomes 2/3. And put 0 here, it becomes 0. And then subtract them, that's your answer. Okay? So it's 2 over 3. So it was not clear that the area relates itself somehow to the notion of primitive functions. Okay? So now This is because of Newton we realized actually this connection, and then we were able to calculate it very easy. So is that understandable? No, but I want to tell you something. I haven't seen them in the books. But if you think a little bit wisely, you can come up with the idea yourself. I want to describe it a little bit why this is expected in the first place. I'm just giving you a naive, a very crude model of what Newton did. Of course, this is a crude model for just motivating you why this might be correct, but the mathematical proof is a different thing, yes? But at least I can make you understand what's going on. Newton realized that this sum, calculating this sum, is very simple if this is a derivative. If instead of f, I have f prime, it turns out that calculating this sum is a matter of seconds. Okay, so I'll discuss about that. Is everything clear here? So none of them you need to learn by heart, but I want you to see that to appreciate the method. Okay, so now let me try to motivate you. Newton, instead of looking at this Riemann sum, he asked himself, I'm just looking up stories, I don't know. So k is going from 1 to n. Let us see what happens if instead of f, I have f prime here. Okay? A function which is written as a derivative of another function. I want to motivate you for this particular choice of function. Calculating this sum shouldn't be that hard. Okay, let us see why is that. So let me draw a graph for you here. So assume that I want to exaggerate a little bit, you can see that. So for example, this is the graph of my function. Okay, and then this is the graph of my function, not f prime. This is the graph of my function. And then let us concentrate here at A up to some point at B. Okay? Now let me ask you this question. Can you answer this? If I draw a horizontal line from here to here, and then I ask you, can you tell me what is this value?
F of B minus F of A.
Exactly. Do you agree? Because from here to here is f of A. From here to here is f of B. But this is f of A. This means that this length is equal to this length. It's a rectangle. And from here to here is f of B. So what is left for me here is f of B minus f of A. Agree? Is that understandable? Okay. Now let me clean this because I don't know how it would be. So this is f of B minus f of A. But let me calculate this. For example, if you go, if you just climb the stairs, if you want to see, if you are on the 10th, I don't know, if you are on the 10th stair, so how you can calculate your height from the ground? One way is to know the height of each one of those stairs and then multiply it by the number of them, yes? So that is an increment, takes you up. So one way of calculating this height is just simply knowing the height of the final point, knowing the height of the initial point, subtract them. But another way to do this is doing a stairwise case. So for example, let me concentrate again on the kth interval. Yes? And let me go up here. And then let me go up. Okay? And then look here. I want to calculate this height. And then I want to do it for the next one. Yes? So if I go to the next one. Yes? And then this is xk plus 1. I want to calculate this height again. Do you agree that if I do calculate these heights and add them together, I will get the same total height? Okay? It is, of course, approximation, but if I make this one smaller, the sum of these increments are very close to this one. And when I send n to infinity, I should expect that these things are the same. So what I'm saying is that instead of calculating the height directly, I calculate each one of these small heights, and then I add these small heights all over. Do you agree that this would be a good approximation to what I want to find? Is that clear for everyone? Now let us concentrate here, and I ask you, what is your idea? Let me call this one delta y. Do you have any idea how can I approximate delta y? Is the question clear? Is it clear that if I add these, it becomes this? Okay? But can you give me, how can I approximate delta y? Yes?
F of k minus f of k minus 1.
Yeah, that seems correct, yes?
Yes, it should be.
Yes, so what you do is it becomes, that's a good way, of course, f of xk minus f of xk minus 1. Do you agree? This is this height, yes? And then what can I do? I can divide it by xk minus 1, and then I multiply it by xk minus 1. So I haven't changed anything. So this is delta y. Let me put an index k because this is for the kth interval. So as you said, you told me this. That's correct. What I did, I divided this by this number, but I'm not allowed to change it, so I multiplied it by that. But, so it's very clear now. What is this one? This is just delta x. Okay? This is similar to the derivative. But it is not the derivative because still this should go to 0. Yes? So this is approximately equal to the derivative. Yes? And times delta x. So this is approximately. Delta xk, delta yk is approximately this value. Okay? Now, if I ask you what is approximate value for this, you would say that I will sum them up. So it means that you sum them up, it becomes sigma f of xk and delta x, and then k goes from 1 to n. And if this is approximately equal to f of b minus f of a, agree? If I want to have the exact equality, what I need to do, I need to write it equal, but I have to send n to infinity. Is that understandable? So this is exactly the sum that I want to calculate. So it was extremely simple, you see. If I want to calculate, if this is the derivative, the answer is f of b minus f of a. Okay? But now, let us see what can I say more. So now do you understand the recipe actually Newton came up with? He realized that if the function is the derivative of some function, then calculating this limit is easy. Limit of sigma f prime of ck delta x, and k goes from 1 to n goes to infinity, is equal to f of b minus f of a. That's it. I don't know why the books haven't talked about this, but this is the idea behind Newton's mind to understand that. So this is very easy to understand. Now, can you just hook up a story now here? You see, whenever you have a function f prime, this should be a function whose derivative you see here, not the function. Okay? Now, can you tell me, from this step to this step, can you tell me what to do? If you understand, you can answer me. Instead of f prime, I put f here. Okay, n goes to infinity. Can you tell me what should I write here on the right-hand side based on this understanding? Yes?
Capital F.
Capital F. Yes? Because you see, if this is f prime, what you write here is f. What is f? F is a function whose derivative you see here. Now, if I give you f, the answer would be a function whose derivative is equal to f. But that is capital F. And that is actually Newton's formula. Is that clear? Okay. Now, these deep things have actually finished, but this was I want you to understand. So it was very elegant idea to guess what will happen if instead of having a function, I have the derivative of the function. He realized that the calculation becomes simple. And in the language that we have now, instead of this f prime, I put f. This f is a function whose derivative you see here. In the nowadays language, it is the primitive function. So that is the formula. So from now on, calculating this Riemann sum is very simple, you see. You don't need to go through that very long steps. You just need to ask yourself, how can I find the function whose derivative is there? If I can solve this problem, then I need to subtract the value of that function in two different places. Okay, is that clear now? Yes or no? Okay, now we can start formally defining a definite integral. Now we realize that this sum is important and it happens in a different parts, in different areas of science and engineering. So it means that it deserves a name. The name of this limit is called the integral. Okay, so I would say that. So definition, now so you need to wake up if you are asleep, if you are in a nap. So now you need to listen, okay? Back to normal. So here, I want to define this thing for you. So definition. And then I limit myself at the level of Math 4 to functions, well-behaved functions. So well-behaved functions in mathematics means the functions that are continuous, so I can draw them with a pen stroke, with one pen stroke, and differentiable without sharp points. But you can talk about integrals for discontinuous functions and even not differentiable functions. Okay, definition. Let f be a continuous function. A function that is continuous on the interval for example, a less than or equal to x less than or equal to b. The integral, let me write, sometimes you need to put this adjective. So let me put it in pair brackets. The definite integral of f on this interval is denoted by, so this symbol you need to learn. So we put this, and then you put a to b, f of x, and then t of x. And it is defined as follows. So what is that? Integral from a to b, f of x dx is the limit of a Riemann sum. Sigma k goes from 1 to n, f of some number in the kth interval. So let me just use it by this letter, this is c, okay? K delta x, and then n goes to infinity. Of course, whenever you talk about limits, you need to add, but this is always for you if the limit exists. But you don't need to be worried about that one. Okay, there are some points that I want to discuss exactly right here. This is very important to understand. First of all, this is not a random choice for the integral. This is a stretched S. And S denotes the sum. Okay? So this is very crucial to understand. Sigma is a sum. Integral is also a sum. But it is in the limit case. When I talk with sigma, you see the index goes districtly up. After 1, it jumps to 2. After 2, it jumps to 3. Okay? So sigma is a discrete sum. But when I send n to infinity, because the number of partition goes infinitely high, it becomes very big. So it means that integral is actually a sum, but more smooth sum. It's a continuous sum. Okay? So if someone asks you why this notation is being used, you would say that this is just a stretched s, a stretched s, yes? But then this is one thing. There are some names for these functions. This function that you see under the integral sign is the integrand. It's called integrand. Okay, so there's a name for that. If you see a function inside the integral, that function is called integrand. And this is called differential of x. And it is a little bit more advanced. You don't need to be worried about that, but you can get a feeling what is that, yes? Because you see, this part, this limit of this sigma is being replaced by this symbol. Yeah, I'm just talking intuitively. And this f of ck is somewhere between x sub k minus 1 up to k. It's just replaced with f of x. And this delta x is replaced by d of x. You can have a feeling what is d of x. What can you say about d of x by looking into this structure? So this integral is this limit when n goes to infinity. When n goes to infinity, what happens for these delta x's? They become very small. So I would say that dx is the smallest possible version of this delta x. It's called an infinitesimal. Yes. So delta x is a finite length. But d of x is that length divided somehow by infinity. But usually when you divide something by infinity, it becomes 0, and it becomes useless, by the way. If this delta x is exactly 0, what is this sum at the end?
0.
It's 0. And then you are not doing any progress. So that is a very important thing here. I am not working with the 0. Because if I work with 0, I get 0, and that's useless. I am working with some mathematics creature called infinitesimal. So it means that if I add a bunch of zeros, the answer is 0. But if I add infinitely many small numbers, it might happen to be a finite number at the end. And that is the idea, very, very important idea behind this notations and things like that. So you have a feeling for d of x. What is d of x? D of x is just delta x when it is very small. It's infinitesimal version of delta x. Is that understandable? Okay. But now one question. Do you think that the integral can be negative? This is a wrong impression that some of you might get because I started with calculating the area. Okay. But that is, I wanted to motivate you. But when you got motivated, if you're a mathematician, you don't care about anything, just mathematics, then you define it abstractly. Now, I'm asking you, can this integral be negative? So let me just ask you one by one. Can delta x be negative? Yes. No, delta x, be careful. Delta x has a definition. It could be negative, but delta x is the final point minus the initial point divided by n. By definition, delta x is always positive, yes? And then, can this integral be negative? Can this sum up? Can this sum produce a negative number? The answer is yes, and I can immediately motivate you. For example, you see I am not calculating the area, I am giving you this function. It's below the x-axis, okay? What's happening? You see, there are many things that you have memorized so far, but you don't need to memorize. If I want to do the Riemann sum for this integral, for this function, what happens? I need to divide this, for example, this is the kth interval, yes, agree? And then I need to construct a table, this value here. And then what is f of ck, positive or negative for this function? It's negative because it's below the x-axis. And this would be negative all the time. So this part is positive. For this function, all of them are negative. So every term inside the sigma is a negative. So I am adding a bunch of negative numbers. It would be negative at the end. So this might happen that the integral is negative. Yes? But then you immediately realize If my goal is to calculate the integral, then I have to face it, it is a negative number. But if my goal from calculating an integral is calculating an area, then I need to understand, should I leave it or I can just do some corrections on that. You see that if this one is flipped up, the area is not changed. So what is the meaning of flipping it up? It means that multiplying it by minus sign. So that is that minus sign that will go out here. So if you remember from Math 3C, you have learned that if some area is below the x-axis, you calculate the integral, but you have to multiply it by a negative sign. So none of them are mysterious anymore if you have a deeper understanding. So do you understand what's going on? If I have this function, this Riemann sum becomes negative, and integral is defined to be equal to that Riemann sum is negative. But if I want to calculate the area, I can imagine that I flip it, the area will not change. I can calculate that for that new function. That would be exactly my area. But flipping, we just learned today, it means that put a minus sign here. If I put a minus sign here, it would be a minus sign there. So this means that if my goal is to calculate an area where this area is above this x-axis, the integral is exactly equal to the area. But if the area is below the x-axis, the integral is negative of that area. Or if you want to calculate the area, you multiply the integral by negatives. So is that understandable now? Yes? And one thing that's also understandable here, what do you think will happen if A and B are the same numbers? By the way, it's extremely important in the setup, A is always less than or equal to B. In principle, it's always strictly smaller. But let us imagine what happens if this is equal. What happens? What will happen here? So it means that I have still my function. My function is the same, extended function. But I start from A and end up with the same A. So what is changing here in this Riemann sum? Can you tell me? What is changing? Yes?
The x becomes 0.
Delta x becomes 0. Yes? Because delta x was what? Yes? If B and A are the same, so delta x becomes 0. These are different numbers, I agree, but delta x is always 0. When I multiply by any number, it becomes 0. When I add them, it becomes 0. So what happens, if someone asks you what is the integral from A to A, f of x dx, it's reasonable to say 0. Okay, so that's important to understand. So, yeah, that is the definite integral. But now, do we know how to calculate definite integrals? Using this formula, because the integral is defined to be the Riemann sum. We learned by Newton that the Riemann sum is equal to this. So now we can combine them, and of course, even though the definition is this one, you can write this formula for the definite integral. So integral from A to B, f of x dx is equal to capital F of B minus capital F of A. If someone asks you what is capital F, I would say capital F is a primitive. You don't need to find all of them. A primitive function of F. Yes? And I can clean it. So you don't need to be careful about that constant C. Why? Do you see why that constant C is not important here? A primitive function is enough, not all primitive functions. Yes?
It's the same, so they cancel.
Exactly, because if you choose a C, this C will appear here and there. They are cancelled. So why we should bother to write it even in the first place? So when your goal is to calculate a definite integral, then what you need to do is to find a primitive function if possible, which is not always possible. And don't think that the function should be so complicated. E to power minus x squared. We cannot find a primitive function of this function according to the elementary functions. We need to artifact a function whose derivative is this. So that's what I'm saying. So still we have limitations, but it is much more powerful than what we realized. We have done it so far. So this is the definition of the integral, but this is the Newton's theorem. Am I independent of understanding this just using that? The answer is no. Because this is an abstract thing. It tells you how to calculate integral. But what is integral in the first place is coming from this Riemann sum idea. Whenever you are facing a problem that needs this, you understand that you are facing an integral, you can formulate the problem in the language of an integral. Okay, is that understandable? It's very crucial. For example, let me give you another example. I give you a wire, a thin wire, and I tell you that the density of this is a constant, the density rho. Usually the linear density is denoted by lambda, but forget about that. I tell you that the density of this length of wire is L. This is very important to understand. So rho is a constant, 5 kilograms per meter here. Sorry, this is kilograms. This is too much, I think. So 0.5 kilograms per meter. Let me just use the linear density. So it means that every meter of this wire weighs, the mass of this 1 meter of this wire is 0.5 kilograms. If I tell you that the length of this is 10 meters, and I ask you what is the mass, you can immediately tell me what's the mass? 5. But now assume that you don't have a good wire. The wire have different densities in different points. So it means that you do not have a good quality wire. So you have a wire whose density is different at different points. For example, this means that if this is the x-axis, if I put this on the x-axis, okay, from 0 to L, then the density is not a constant number, it's a function of x. It changes from point to point. Now I ask you the same question. What is the mass? What is the mass of this wire? This is extremely important. So you see, if you want to solve this problem, Newton's formula doesn't help you at all, because you cannot feel the connection between this problem and an integral in the first place. Newton's formula becomes interesting and important when you discover what you want to solve is related to the definite integral. Otherwise, why should I think about that? To understand that the problem that you want to solve is related to an integral comes from your understanding about the Riemann sum. Whenever you want to calculate something which relates itself to the Riemann sum, then it is a definite integral. Then Newton told me how to solve it. Yes, please?
I have to go think of that.
Yes? Okay, so can you tell me how can I solve this one now? This is extremely important. When you want to go to the university, if you want to do electrodynamics, everything, mechanics and everything, you need to have an understanding that how connect this problem to a definite integral, then use Newton's method to solve that definite integral. Going from this understanding, finding this connection is coming from this understanding. Okay, so can you tell me how can I solve this problem? I want to teach you. So this is the idea. I would say that even though this is changing, but let me concentrate on a very short interval on this wire. Extremely short interval on the x-axis is denoted by infinitesimal dx. Instead of delta x, in principle, dx is so small that you cannot recognize the difference between endpoints. I'm exaggerating, okay? And now, do you agree that I can talk about the density at this point? Because the density at these points are essentially the same because they are so close together. So I can talk about the density at this point and then multiply it by the length. What does this give to you? Rho x is the density at this point. Because this is so short, I can imagine it's a constant. and I multiply it by the length, it gives you what?
The mass.
The mass of this very small bit. This is as infinitesimal. And then mass usually in physics is denoted by m. Infinitesimal mass is denoted by dm. Okay? And now, if you know the mass here, and then the mass here, and then the mass here, if I ask you what is the mass of the whole thing, what do?
The sum of the
You sum them up. But this is not a discrete sum. It's a continuous sum. So instead of putting sigma, you put integral. Because that's a sum again. But it goes from 0 to L. Okay? This you cannot understand this part, so it means that your m is this value. You cannot understand this by Newton's formula. Newton's formula tell you how to calculate an integral. But you need to set up an integral in the first place. Is that understandable? Now you see that I am calculating the mass. And you can think about all of these things. So if you want to add infinitesimal quantities together, you need to think about a definite integral. Is that clear? So what problem you are facing, I don't know. If you can model that problem in the language of adding infinitesimal, it means that you are facing an integral, and you don't need to be worried. Hopefully, you can solve it using Newton's problem. So it's extremely important to. What's the time, by the way?
We have 20.
Yeah, we have 20. Okay. So that is the problem that you want to solve. Okay. So, for example, you can also have another problem. This is, I would say that this is very important to understand, because you can improve your skills here a lot by solving a lot of problems. But finding the connection of the integral by that is probably important. So, I don't know, we have a lot of actually these kinds of problems. So I don't know how much have you studied electricity. Do you know the potential of some charge or something? Yes. So for example, if I have a point charge here, and for example, say Q, and I want to find the potential R units distance away from that point. So I think you have seen the formula, yes? So assume that this is the distance. I don't know, how do you denote potential in your book? V or phi?
V.
V. Okay. So I am asking you, what is the potential due to this point charge there? What is that? So you don't remember.
No.
But I can write. So do you write this 4 pi epsilon 0? Have you seen something like this? Yes. And then you multiply it by your charge and then divide it by the distance. So this gives you the potential of this point at this. Okay? But point charge particles are artifacts. In reality, we probably don't have them quite so much, yes? What we have a finite charge distribution, usually. Okay, so for example, what I do, I would do this. If I give you a wire which is uniformly charged, okay? So which is uniformly charged, and you want to find, I don't know, for example, you want to find the potential of this extended wire at this point. So what you can do here, I want you to understand the deep connection. Integral comes to your help. Yes? Do you have any idea?
You divide the wire and take the...
Exactly. So what you say, you divide this into very small pieces so that you can find the potential here, because you know, if I make it very, very small, it means that it is a point charge, and then I can use the formula for the point charge to calculate the potential here. So what would it be? It would be 1/4 pi epsilon naught, and then this little charge is denoted by the infinitesimal dq, and then divided by r, this distance. Okay, but this doesn't give me the whole story. This just gives me a very small portion of the potential, which is coming from this small charge. And now if I want to have all of them, it means if I want to find this, I need to set up an integral. Of course, this integral could be more complicated than that. But this is the idea, you see? So you can cook up a lot of things, So if you want to add infinitesimals together, if your problem relates to adding infinitesimals, you need to think about the integral. And then the most effective tool for calculating the definite integral is this formula on the board. Okay, so hopefully you have now a good understanding of what's going on about integrals. But now let us improve our skills now. Okay, and I think improving, there is nothing to improve here. Because what is the hard part of this calculation? What do you think? What is the hard part? Yes?
Finding
The primitive function is the problem. Because if I give you the primitive function, what you need to do is to put these numbers in and subtract them. So you see that calculating a definite integral, I wouldn't say is a problem if you know how to find the primitive function. But deeper understanding of the notion of integral is very important. Okay, now let us try to solve some problems together. Any questions here? But of course, this is from electromagnetics, this is very different because this R also depends where this particle is. The distances are different. So you need to take care of all those things, yes? But in general, this is the idea. Okay, so let us solve some problems. I don't know what problems. So let me just give you some examples. Example. Determine the exact value of the following integrals. I don't know. Let us start with the simplest possible problem. So number one, integral from -1 to 3 x to the power of 2 dx. So let me write it. Let me make these minus signs more. So from -4 to -3. Yeah. First of all, is it reasonable? Because when I write an integral, I think that A, the lower limit, is smaller than the upper limit. We will come later what happens if this is the other way around. That just needs a definition. This is not something that you can visualize. So assume that I want to calculate this integral. By the way, I forgot to write, this is called the lower limit and this is called the upper limit. This is the integrand and this is the differential, okay? Now I want to calculate this integral. Can I use the Newton's? So here, you are not at the level to discover the connection of your problem with the integral. Integral is directly given to you. So what you need to do is to find the primitive function for this. What is the primitive function? Is 1/3 x to the power of 3. And there are some punctuation rules that you have to respect. When you finalize the process of finding primitive function, you are not allowed to put integral sign again. Okay? What we do, we put a vertical line in front and we write from -4 to -3. If you write integral here, I will give you 0 points. So please respect that. When the process of finding the primitive function is finalized, you are not allowed to put the integral sign. If you cannot calculate it immediately in your head, most of the time we can't, we have to put a vertical line in front. So be careful, okay? These are the punctuation rules that you have to respect. And then according to this rule, I have to calculate this function for the upper limit. I have to calculate the same function for the lower limit, and then I subtract it. My experience is that some students mess up these negative signs. When I teach it, I prefer to teach it in a way. So I do this, I put -3 here, patiently calculate that. So what is the answer? It's -9. Then I put -4 here. So it becomes -64/3. When these are separately done, I go back to horizontal line. That's up to you, of course. I write the number above minus the number below. So this decreases the chances of messing up these negative signs. That's up to you. It's not mandatory. So then what happens? It becomes negative 9 plus 64 over 3. Then I don't know, it becomes 64 minus 27 is, if I am right, 37 over 3. Am I right? Yes. Is that understandable? So you see there is no problem. So actually the hard part is calculating the primitive function. Okay, so I don't know. I think this is very boring to solve this. It's not boring to find, because this is actually a very favorite subject of mine, to find primitive functions. They could be really, really amusing. But let me give you another example. So number 2. So for example, let us calculate this integral from 1 to the Euler number e. And let me write it in this way: 3x squared plus 2x plus 1 divided by x dx. So you want to calculate this. So whenever you see this, you need to focus on finding a primitive function. So you need to review your lessons about finding a primitive function. Okay, can you help me to do that? Can I directly find a primitive function for that?
No,
So what is the first step? Yes?
we split.
Split them. When you are splitting, you have to keep the integral sign. This is the reason that I'm. So you need to. So you are not allowed, because when I am splitting, I haven't started the process of this finding a primitive function. So you have to keep the integral sign. If you are lazy, then I will be lazy to give you marks. Okay. So you have to write 1 to e. And then you need to start. If you are quick, do it quickly. If you are not, just do it patiently. Okay? Okay, so here dx. But then you need to simplify. So simplification is still not the process of finding a primitive function. So I have to keep the integral sign. I have to. Then it becomes 3x. 2x over x is just 2. And if you remember your lessons from the primitive function, you know that you shouldn't move it up, because 1 over x is ln of x, the primitive function for 1 over x. Now, I want to start here. Here I am starting finding primitive function. I have to remove integral sign. A primitive function to this is 3 over 2x squared. A primitive function for 2 is 2x. A primitive function for this is ln of x. And then instead of that, you have to put. So you see, I'm just mentioning over and over, you have to. This is the correct way of writing. Now, this is up to you. I would recommend you, at least for the few problems, just do it, not to make mistakes for nothing. Okay, so I will put the upper limit there. So it becomes 3 over 2e squared plus 2e plus ln of e. Because I have asked for the exact value, you are not allowed to use calculator for putting these numbers. You have to keep it in that way. But from your knowledge about ln, you know that ln of e is exactly 1. So then you have to write this. So this is 3 over 2e squared plus 2e plus 1. And then I go and put 1 here. It becomes 3 over 2 times 1 squared plus 2 times 1 plus ln of 1. But everything can be calculated here. 3 over 2 times that is just 3 over 2. And then 2. What is ln of 1? 0. So I don't write, but I calculate. What is the answer? It's 7 over 2. And then when everything is done, I go back to horizontal line. I write what I got above minus what I got below. And then if necessary, do some simplifications. So here it is 3 over 2 e squared plus 2e, and then minus 5 over 2. So that is the exact value of your integral. Okay? So, am I making mistakes?
You forgot the ln of 1.
ln of 1 is 0.
Oh.
Yeah. ln of 1 is 0. Yes, I'm right. Yeah. ln of 1 is 0. Okay, so this is a number. So remember, let me ask you something like this. If I give you this in the test, the same function, and then I ask you find the derivative, what's the answer? The same integral, I was lazy to write it down, but that's the same integral of the derivative. What's the answer? Immediately, 1 second. You don't need to calculate it, it's 0. Why it is 0? Why is it? So, are you confused? I talk so much, yes. Because it's a constant number. As simple as that. The reason that I was telling you, any definite integral is a number at the end. So if I want to take the derivative of that, it becomes 0. It doesn't need any calculations. But if I give you something like this, and I ask you to take the derivatives, can you tell me, at the end of this calculation, do you think this will depend on x or on t?
X.
On x, yes? Because if you want to calculate it, the primitive function, this tells you that my variable is t, so it becomes t to the power of 3 divided by 3. You put 1 and x in front. So if you calculate, it becomes x to the power of 3 over 3 minus 1 to the power of 3 over 1. So it's a function of x. Now, if I ask you calculate the derivative of this with respect to x, it is not 0, because it means that you calculate, you get something in terms of x, and then you differentiate from that one. But if I give you two of them numbers, who cares? Because at the end, integral is a number, and the derivative of any constant number is 0. You don't need even to calculate, yes? Okay. Okay, so I stop here. I think that is good. And then, so let me say goodbye to people who listened here. Thank you very much. I don't know how many of you were at home. So I end this stream.